All right, I thought it might be worthwhile to point out some interesting details about arc cotangent or inverse cotangent. So let's just call this the special case of arc cotangent, or what we call, what I would usually write as COT inverse of x. Now let me remind you of the graph of cotant inverse of x. Y equals COT inverse of x. And of course, it has a bunch of asymptotes. It looks to me like every multiple of pi, it has a vertical asymptote. And obviously it's not one-to-one. It doesn't have an inverse, so we have to restrict the domain. So in order to do that, every single textbook I have ever used does this. In order to define an inverse, they always restrict the domain, of course, but here the domain is usually restricted to 0 to pi. So we say the domain is 0 to pi, and the range is negative infinity to infinity. So then when you flip it about the line y equals x, you get something. So the normal inverse for us is f inverse of x equals cotan inverse of x, and the range is from 0 to pi as matching the domain of the original one. So the range equals 0 to pi, and the domain is all real numbers. So this is the way it's done in every single book. The derivative, no matter what I say in this, is not going to change even when I show you what computer and calculator manufacturers have decided is a good idea. I wasn't aware of this until I started playing around with the graphs on a calculator to find out that what computers and calculators do is not this. They actually stray away from textbooks in what they do. Let me show you. So anyways, this, I'm going to call this is the way we will proceed. And what way is that? That's the way I just showed you here. The stuff up here, this is the way we will proceed. So what I'm going to do next is not what we're going to do. Here's what calculator and computer software do. The way they restrict it is completely different than I would have expected. What they do is they take this piece right here that goes up to infinity but comes down and hits the x-axis at pi over 2, and they take that as one piece. I'll put a dot there. Then for their other piece, to complete the whole part, they take this piece down here, except they don't take this point here. They leave a hole there. The reason why is because if you're going to have an inverse function, you've got to pass the horizontal line test. So if they had a dot there, they wouldn't pass the horizontal line test. So what they take then, they take this part. I'll see if I can. They take this piece right here, circle it, and then they take this piece right here. And this is what they get. So they have y equals cotangent of x as normal. But then here, they've restricted the domain differently than any textbook does. This is what we'll call f of x equals cotangent of x, the one that we're trying to get an inverse for. And keep in mind, I'll put a dot here, a solid dot here, but a hole will appear here. Okay. Then, when you flip it about the line y equals x, this is what you will get. So I'll kind of put them on the same page here. You have, for their version of cotangent of x, you have the domain is negative pi over 2 to 0, union 0 to pi over 2, but it includes that one. And the range is negative infinity to infinity. Now when you flip it about the line y equals x, this is the version of inverse that is used by calculators and computers. There's some problems with it that I really don't like. You have, for one thing, it's not differentiable at the origin, and the version that the textbooks use are differentiable at the origin. See this? Look at this. Differentiable at the origin. It's nice and smooth going through there. In fact, cotan inverse of 0 is equal to pi over 2. So in their version of things then, this has a solid dot here, but then has an open dot here. So it has not just not differentiable, it's completely discontinuous at that point. And plus, look at these. That is a most ridiculous domain because you're counting one point but not the other, and the range is fine. I don't have a problem with that one. This will not be used. What happens is this. You have tan inverse of x plus cotan inverse of x is going to equal pi over 2 when x is greater than or equal to 0. But tan inverse of x plus cotan inverse of x equals negative pi over 2 when x is less than 0. And this, to me, is probably the reason why we don't want to do it, because CO stands for complement. That means the two, remember, these give angles. The two angles should add up to pi over 2, like this. Now, if instead you take the version that we accept, I suppose, in the mathematical community, if you look at our version here, so what you can do to combat this, I'll show you. You'll see it's everywhere. If I go to, I checked it out several places. If I go to online, I go to wolfram.com. That's what they do. Here, I'll even make it bigger so you can see it. That's about negative pi over 2, and that's about pi over 2. That's how they do it there. If your calculator even bothers to have the function built in, like mine does, they do the same thing. For the life of me, I can't tell why. I'd be sort of interested to see, though, if I start to move this over, it gives me, it gives me pi over 2 when x is 0, so it doesn't try to do this one. It does this one. There's so many loopholes and things to deal with in these, it's not even funny. So, what you can do, there's no need to really combat it. To be honest, if you ever actually solve an equation using cotangent inverse in your life, I would be amazed. If the way we should deal with it is this way, because it has all sorts of symmetry to it. Your best bet is to do this. Define each of your cotangents, or your co-inverse functions. Let's say I do cos inverse of x. Just define it to equal pi over 2 minus sine inverse of x. Sec inverse of x equals pi over 2 minus cosecant inverse of x. I got that backwards. Come here. I'm defining the cos. the complementary angle, basically. We'll do cosecant inverse of x equals pi over 2 minus sec inverse of x. And so cotan inverse of x equals pi over 2 minus tan inverse of x. Once you do that, you can ignore all of this stuff. Although you have to be aware of this kind of stuff when your calculator does things to you. But honestly, most calculators don't even bother to have an arc cotan or an arc secant or any of the other things. You can get away with inverse sine, inverse sec, inverse tangent for everything. You probably don't even need this one here. Inverse sine and inverse tangent will do everything you need in your entire life. Let me show you why the cotan inverse is not such a bad thing. Because ultimately, you will have some sort of an equation to solve, something like cotangent of x equals, I don't know, let's just say a. If I want to find out what x is, you'd normally take cotangent of x. But what you could do anyways, tan of x will simply equal 1 over a. And then if I want x, I can just take the arc tangent. So that's easy enough to work with. You don't even have to ever work with cotangent ever in your life if you don't want to. And in fact, what they do, what the authors have done, or what the calculator makers have done, is they have defined cotan inverse of x to equal tan inverse of 1 over x. And they're interpreting that if you plug a 0 in for x, which is undefined, but the limit as x goes to infinity, tan inverse of x equals pi over 2, they are interpreting if you plug a 0 in for x, then you'll have an infinite expression in here. And they're saying, well, make that equal to pi over 2. Well, there's a big problem with that as well. Because to even work this, this does not have a two-sided limit when x goes to 0. It will go to positive infinity from the right and negative infinity from the left. So what do I say about all this stuff? Let me see if I can get it all in one picture. I can shrink this down a little bit. All this stuff that the computer and software makers do, there are ways around it. You can deal with it without having to be wrong according to the textbook. All of this is wrong. We are instead going to use the one that all of the textbooks, including our own, every textbook I've ever used, has worked it this way. So keep those in mind. If you ever have to use cotan inverse, then you could. I could have them on tests, things like that. You do need to deal with them occasionally, but usually you can get around it. But sometimes you have to draw the graph and things like that. So with that in mind, the easiest thing to do is this. Define all your co-inverse functions this way, and you will be good to go for this course.